Hello, everybody. Welcome to the third, and it's an optional lecture on GRAND. Today, we're going to cover some of the more mathematically oriented aspects of GRAND. Again, this is not necessary to understand the bulk of the algorithm, but if you're interested, I very much hope that you will stay and listen to these materials. Going ahead, let me start by sharing our slides. And I'd also like to point out that I should have, but it's fine, we're going to be doing it now. I shared the website for GRAND, which has all of the papers, which I think will be of particular interest for those of you who maybe took this took this class and decided to look into this in more detail. So with that, I'd like to encourage you, if you're interested, to go to this website, Grand Decoder. .mit.edu, you will find a complete list of the papers, and in particular the more theoretical papers, of which I will give a flavor in today's lecture. So for the sake of review, let's remember what we had, these principles of coding, where we have here that we're going to be doing guessing over the noise. So remember, GRAND is doing guessing over the noise, and it's particularly using the fact that we have a number of noise strings, which with high probability falls within a set of cardinality to the NHN, because this is sufficient cardinality size to encompass the entire typical set, and therefore it also encompasses the to the NHN most likely strings, which of course, since they're the most likely, strings are at least as likely as the typical set, which is of the same size. And therefore, since the typical set has a probability that goes to 1, the set of to the NHN most likely strings also has a probability that goes to 1. Now, when we were discussing the behavior of GRAND, I mentioned briefly the issue of Rényi entropy, in particular talk to you about Rényi entropy of order 1/2. And I said that we would talk more about that topic for those of you who are interested in this optional lecture. So this is that optional lecture, and I want to give you this definition. The Rényi entropy is defined in the following way. So up until now, we've seen the Shannon entropy where there is no subscript here. But this subscript here, in general, is called the order of the entropy, okay? What you will see is that this is the definition of the Rényi entropy, where the set A here, math boldface A is actually the set of possible, the alphabet from which any random variables samples are taken, okay? So at this point you might say, well, this is a little funny because last time and the first lecture we defined the Shannon entropy. It didn't really look like this at all. Well, actually, if you set alpha to 1, which of course wouldn't work by just plugging it right in because we have this term here, which doesn't allow alpha to be 1. But if we were to take the limit of this Rényi entropy of order alpha in the limit when alpha goes to 1, this actually would get back to the Shannon entropy. You can play around with it on your own and check that out. But basically what happens here is that you're looking at this alpha, which is affecting the moment, And then this 1 minus alpha is in effect doing some appropriate normalization. So why is the Shannon entropy of interest to us? Well, we saw that it is helpful for determining mutual information, that it's helpful for determining the typical set. Why is Rayleigh entropy interesting to us also? Other than the fact that it is inherently a generalization of Shannon entropy. Well, let's look at the moments of the guesswork. So if you recall what we saw previous lecture, the guesswork here is the random variable, which is the number of guesses before I guess, when I'm guessing from most likely to least likely, the correct realization, the correct occurrence of a string, in this case, the noise. If I look at the log of the expectation of the alphth moment of this guesswork, okay, so think of moments. We know that thinking of moments, when you take the mean, it's the first moment. We know by taking the second moment, when we compute, say, the variance, when we compute the kurtosis, we look at the fourth moment, but we can, of course, look at any old moment. Let's look here at taking the alphth moment. We have that the log of the expectation of this random variable raised to the alpha is given by the following, okay? And it's alpha times the entropy of 1 minus 1 plus alpha. I'm not going to go much into what H min is. Those of you who have been studying some issues around security may have seen that H min. The reason I'm not going to be that interested in it is because we're really only going to be looking for alphas in this region. Remember that in Arakan's work that I mentioned on sequential decoding and how he had looked at um, how the cutoff rate came about, basically he had actually shown that when alpha is 1, which means that this would be 1 and this would be 2, that actually 1 over log of the expectation of g to the n goes to 1 over h1 h over 1 half, h of Rayleigh entropy of order 1 half, and that Rayleigh entropy in that special case when we're looking at the expectation of the guesswork was a really important parameter, a really useful parameter in order to show what the behavior was of the system. And it was from that determination, that investigation, that he was able to show that the cutoff rate, which was the practically achievable rate, say in a binary symmetric channel, was equal to 1 over 1 minus h1 half. Okay, this Rayleigh entropy of order 1 half. That gives the mean, scaling of the guesswork, the mean is when the alpha is 1. H of 1 half, as we've mentioned before, and I encourage you to play with this a little bit on your own when you're studying your notes and convince yourself of this. H of 1 half is generally greater than or equal to H, which again, we could think of H of 1, but we cannot write it as 1 because remember this would not actually be 1. H, the Shannon entropy, is this limit of H of alpha when alpha is going to 1. I encourage you to look at the works that are referenced here if you want to find out more about it. But in particular, one of the things we're going to be looking at is this last work with Mark Christensen, the student of Ken Duffy, co-inventor of Grant, which looks at these looks at the behavior of these moments and does the following thing. So, we know that the first moment, second moment, so on. If you can find a whole lot of different moments and you can verify certain constraints, certain conditions, you can actually not just go from using a distribution to find the moments, but you can use the moments to approximate a distribution. And that approximation of a distribution through the moments can be done using a principle of large deviations. Okay. Okay, so let's look at that a little bit more closely. So as we just mentioned, it is the case that we have this sort of behavior. And here's by the way, here's the definition of H min, which is basically when the alpha is going to infinity. Again, not going to go much into the meaning of it, but there is a meaning of it. But basically what happens is if I look at these different moments and I look at this log and I call this lambda n, if we assume that this holds, which was shown under a variety of conditions, again, I'm going to refer to the papers, and if the derivative is continuous on this range, again, we don't need to look at the full range. We're really not going to go look below 0 for alpha, but it doesn't really matter. Then we have that this satisfies a large deviation principle, okay? Which means that we're going to have a rate function. And when we look at this rate function, okay, we're going to look at this rate function. We're going to have the rate function, which is going to have the following expression. Again, remember that this lambda sub n alpha is really given by this limit here, okay? Which we know what the behavior of that limit is. So we're going to have that it's a soup over all these different alphas. So we're going to basically need to be able to range the alpha, which is why it's important to have this for arbitrary alphas, x alpha minus lambda sub n of alpha, okay? And we know that if the x happens to be 0, this soup happens at h min, okay? And we know that if the x happens to be the Shannon entropy h, then this is going to be 0. Okay, so basically this, the rate is going to hit 0. I'll show you some figures later which will illustrate this rate hitting 0. Okay, so why is this interesting to us? Let's remember what we're doing when we're decoding. I have a race between two different guesses. We have the guesses, which are, we have the guesses which correspond to the code word difference noises. Remember, these were the noises that would take us from one code word, from the received system, to another code word. Okay? So I received a Y, and what is the noise that would take me from the Y that I received to another code word, which was not the code word that was transmitted. Assuming that all the code words are uniformly identically distributed because we have uniform distribution of the inputs and our code book was itself selected in a uniform way, the way I showed before, where we dip each time with replacement in the bag of 2 to the n possible code words. Then what's going to happen is that I'm going to be guessing for all these, for the length n code words, I'm going to be guessing over all of the code words that are not the one that was sent, okay? And as I mentioned, these strings are going to be uniform random variables over whatever alphabet I'm working on. In the examples that we have shown in our previous lectures, this cardinality of A, if we were in binary, for binary, this was 2. Okay, for the binary alphabet, but in general, it could of course be a larger alphabet. That really does not affect the logic of our arguments. Okay, all right. So we have all of these code word different noises. Okay, and how do we define R, the rate that we talked about before? Well, let's go back a few slides. Let's go back a few slides. Let's remember that this R here was representing how many messages there were. There were 2 to the NR strings that were valid messages out of these strings of length 2 to the N. In the case where I have an alphabet of size A, then obviously I'd be looking here at A to the NR strings. Okay, that would be the size of my message set. Okay, so if we consider then what's happening here, this is, so maybe erase this and write it over here. Basically, this log mn here, this is actually going as log of, in between these parentheses, I could have rewritten this as A to the NR. The earlier example there we showed this cardinality of A just happened to be 2, okay, because we were looking at binary. That was, our alphabet size was just binary. Okay. So basically, log of mn, which is the number of actual messages of n letters, of n symbols from the alphabet A, this log of mn is R. It's just like the R that we saw before. Okay, so this is indeed the definition of our rate. Okay, now here you can argue there's only mn minus 1 code word difference noises, because one of the noises, of course, leads to the correct message. That's fine. Because we don't want to fuss too much with it, I'm going to forget about that -1. In any case, it's a conservative assumption. So we all in agreement that actually the code word difference noises, there is mn minus 1 of them. not actually mn, but we going to just add an extra one just not to drag this -1 around. Okay, and because of the construction, so this ID uniform aspect here, as I mentioned, this is coming because of the construction of our code book in the random way. Construction is ID. Construction of code book is ID. Okay, so that's coming from the construction of the code. Okay, so we have all these noises, no code word difference noises, that we could be guessing, which would all give an error. And we only have one noise that we could guess, which is going to lead to the correct decoding. Okay? Now, of all the possible code word difference noises that could be guessed, which one do I need to worry about? I only need to worry about the one that would be guessed first. Okay? Now, the correct code word difference noise, by the way, is the true noise. It does not have this ID uniform distribution. Only the code word difference noises have this ID distribution. The true noise has the distribution of the noise, n, which is not going to be ID, say in the binary case, equally likely to be 0 or 1. Let's think what would happen if our noise in the channel were ID uniform 0, 1. In that case, we would have a binary symmetric channel with probably 1/2 of crossover, and the capacity of that would be 0. We would have no chance of decoding correctly, or we would just have a minimal chance of decoding correctly. So it's very important that these only the code word difference noises, okay, I'm going to emphasize that, only the code word difference noises have this ID distribution, okay? And the ID uniform distribution comes because of the random construction of the code book. All right? So this is going back again to the construction that was given to us originally by Shannon. Okay. Now, if I look at this U of n, what's going to happen is that I can look at the 1 over n log of the U of n, and it will have a rate function. Again, why do we call this rate function? Because if I were to take the exponent on both sides, if I were to raise this to an exponent, then what I would get is I would get e to the 1, if I were to take the exponent here of I u of x, okay, I'll look at that exponent of I u of x. What does that give me? Well, it would give me u of n, okay, because I would have the exponent here, e1, it would give me the u of n, and then I would have the 1 over n, right? So I think of actually taking, it's easier to do it this way. If I take e to the n I u x, then that gives me 1 over n, right? So you can see why this is the rate. This is showing me how this u of n is going with n as weighted by this IU of x. Okay, so this is why the IU of x is a rate. Okay, not to be confused with this rate R. Okay, this is a rate of growth. The rate R here is in effect a rate of growth. You can see the same behavior, right? If I take the exponent of this, then basically what's happening here is that you know, Mn is going to be equal to some, you know, exponent times something n, which is growing as R. Okay, just to be a little bit careful here, I have to basically maybe just as a little bit of a difference in that I'm really taking, instead of an E, I am taking this A, okay? Right, so here's A, here's E, but you see in both cases these are, so you can see why we call this rate and this is rate. It's just when we call the rate of a code, we really mean this rate. And here it's the general concept of rate that you would have learned in any area of engineering or mathematics, not necessarily in communications. Okay, so this is a rate, this is a rate. Why are they a rate? Because they're showing how your quantity of interest is changing in the exponent with this length n. Okay, so I really want us to think about this code of difference noise. And now what I haven't shown you is that this holds, okay? But let's not worry right now about that. Let's just progress a little bit. And what happens here? Well, what happens here is the following. I have this rate function for this code word difference noise, okay, which is this IU of A. And when do I make an error? I make an error if I guess the true noise. So this is guessing the true noise. Okay, this is guessing the true noise. I make an error if I guess the true noise after I would have guessed the minimum of the code word difference noises. Okay, which means that this U, which was the time of guess, a minimum out of guessing all these uniform code word difference noises, if this U were to happen, this guessing would to happen before I would have guessed the true noise if I just went down the list of possible noises from most likely to least likely, which of course eventually will allow me to guess the true noise if there were no other noises, no code word difference noises, right? So for instance, if I only had a single possible code word, I would eventually guess the true noise because I would go down all the possible noise sequences, and only one of them would eventually get me to the true noise. So with that in mind, this is basically when I will make an error, okay? And we can show that it's this infimum of these two elements. This is the guessing of the code word difference noise. And this is just so this is the rate here. This is the rate of that went with the code word difference noise. And this is the rate of growth of the guessing that goes with code word difference noise. I'm going to call it code word difference noise. I'm just going to shorten it. And this is the rate for, this is the rate for the noise, the true noise, the noise that actually happened on the channel. Okay? And the probability of the maximum likelihood decoding is not the transmitted noise. It's going to decay basically exponentially in the length n. Why? Well, this is positive, and this here, there is a minus. So when I multiply by n on both sides, you have to be really careful because of the limit. But basically what's happening is, you know, this is negative, which means that this is the rate of this probability is going to decode exponentially the block length n. How should we think about it? Let me forget about the limit right now. Let me just assume I have a very large n, and let me put approximate equalities. What I have is that e, I'm going to take natural log here, okay, e to the minus n times this expression. Let me draw this expression here in green. Let me call this for the time being rho, okay? E to the minus rho, okay, is roughly going to be equal to, okay, the probability of an error, which this is the probability of an error is, which is that I guess a code, the first guess of a code word difference noise occurs before the guess of the actual true noise. Okay, so this is a definition effect, our probability of error. So this is a way of actually finding what we call in information theory error exponents, okay? This is finding an error exponent. The exponent is again this notion of rate, which is how something is growing or decreasing with how something is growing or decreasing with the length n. And what we see here in this error exponent is that this is showing us that the probability of error here is going to 0 because this is positive. This row here is positive because with the minus it's negative. This probability of error is going to 0 exponentially with n. Okay, this is similar to how we compute error exponents. You can see Gallagher's 1968 book, but of course this actually gives you much finer representation of the error exponents. Let me take a second here and go over what are some of the schemes that you can then describe in terms of behavior. I will take a brief break here, and we'll continue the second half of this lecture.